Guys, welcome back to part 2 of absolute value functions. Just wanted to post the agenda here so that you can see where we're at. We're watching right now the video on absolute value functions part 2. Wednesday is our review. Thursday is your module 4 test. And Friday you will have to complete any missing assignments and be sure to complete your 10 topics. And then we will not be back in session until January 4th. So just wanted to make sure I went over that with you before we get started in this lesson. So in part 1, we were talking about translations, transformations in general, but specifically the translations shifting right and left, up and down. And so today we're going to look at a different type of transformation, and those transformations are dilations and reflections. So let's begin with dilations. When we multiply the absolute value, or when we multiply the problem after evaluating an absolute value function, this creates a vertical change. So if the absolute value of a, whatever this number is that we're timesing by, is greater than 1, then it stretches my graph vertically. But if that number, when I take the absolute value of it, falls between 0 and 1, then the graph is compressed vertically. I think of it like being smashed down. When you smash something down, think about if you have a ball of Play-Doh and you compress it from vertical compression, top and bottom, you're smashing it out. What happens? It gets wider. So this is a dilation. There's also the dilation that can occur if we take an input and multiply it by an absolute value function. This creates a horizontal change. Again, if that number is bigger than 1, then the graph is this time compressed horizontally. And if the number falls between 0 and 1, then it is stretched horizontally. Okay, so let's describe the dilation that occurred in the function g of x equals 5 halves x as it relates to the graph of the parent function. So you can see here on my graph, I have the parent function in red, and then I have this blue function that is the g of x. So what happened when I multiplied the absolute value by a number greater than 1, right? 5 halves is greater than 1. So if I come up here and I'm not doing the input, I'm not multiplying inside the absolute values, but I am multiplying after evaluating the absolute value by a number greater than 1, we can see that our graph is stretched vertically, and that is exactly what happened here. The red was stretched vertically and by a factor of 5 halves. So what happened was my slope got steeper. Okay, so let's describe the dilation in g of x equals the absolute value of 2 of x as it relates to the graph of the parent function. Well, by following our rules, if we scroll back up here, this is the input is being multiplied by a number that is greater than 1. So we would expect it to be compressed horizontally. Compressed horizontally. So if you think about compressing something horizontally, I'm squishing it together, a compression this way from the horizontal side. From each side, I'm compressing it. So it's kind of like a vertical stretch. A horizontal compression looks like a vertical stretch. And let's prove that here. So let's plug it in. If I plug in -4, 2 times -4 is -8. I take the absolute value of -8 and I get a +8. So when I plugged in -4, I got, let's see, can't see if I write in white on white, can you? I get out an 8. Okay, if I plug in a -2, 2 times -2 is -4. I take the absolute value of -4. Remember, I'm just asking how far away from 0 is -4. It's 4 units away, so that answer is 4. 2 times 0 is 0, absolute value of 0 is 0. 2 times 2 is 4, absolute value of 4 is 4. So let's go over here and graph our function. So we can go over -4, up 8, go over -2, up 4. 1, 2, 3, 4. Go over 0, up 0, so the vertex remained the same. And I go over 2 and up 1, 2, 3, 4. And we could see that if I was to plug in a 4, 4 times 2 is 8, so I would go over 4 and up 8, even though I didn't write that out. So we can see that, yes, this looks like a vertical stretch, or we can think of it as a horizontal compression. We're compressing it from the sides, so it's stretching it this way because I multiplied inside of the absolute value. All right, so let's describe the dilation that would occur here. This time it's outside the absolute value, and that value is between 0 and 1. So that tells me that it's going to compress it vertically. And we can prove that by plugging in the numbers. The absolute value of -6 is 6. -6 times 1/3 is, or absolute value of -6 is 6. 6 times 1/3 is 2. Absolute value of -3 is 3. 3 times 1/3 is 1. Plug in a 3. 3, absolute value of 3 is 3. 3 times 1/3 is 1 again. And again, when I plug in 6, I'm going to get out 2. So let's graph it. I go over to -6, up 1, 2. We can see it's wider than the previous function. Go over to -3 and up 1. If I plugged in 0, I would get 0. Go over 1, or over 3, I mean, up 1. And over 6, up 2. And there is my graph, and we can see that it was compressed vertically. Smashed down, like smashing it down. I compressed it vertically. All right, so now let's look at some reflections. Reflections occur when we multiply by a negative number. So if we multiply the entire function by a negative number, it's the reflection across the x-axis. If we multiply inside, we multiply by the x value, the input, by a negative number, it's just the reflection of the graph across the y-axis. So we have negative times the absolute value reflects it horizontally, or reflects it across the x-axis, not horizontally, it reflects it across the x-axis, and multiplying inside the absolute value reflects it across the y-axis. So let's look at some examples so this will make sense. This has several translations. We know this +3 is going to take that vertex and shift it to the left 3 units, right? To the left 3, and that +5 is going to shift it up 5. However, there's also this negative to take into consideration. So let's plug in some numbers and try it. So if I do -5 plus 3, -5 plus 3 is -2. I take the absolute value of -2, I get a +2. But then I have this negative out here, so now I have -2 plus 5 gives me 3. I said all that kind of fast. I'm going to write it out here so you can see what I'm talking about here one more time. We'll do it with the -4. So negative, absolute value of -4 plus 3, and then plus 5. So -4 plus 3 is -1. But when I take the absolute value of -1, I get a +1. But then I have this negative outside of here, so I have -1 again. So -1 plus 5 is 4. Plug in my -3. Let's just erase this and plug in a -3 here. -3 plus 3 is 0, so then add 5 and we get 5. Okay, plug in a -2. -2 plus 3 is a +1. +1 times -1 is -1. -1 plus 5 is 4. So again, we get out a 4. So let's graph it. We go over -5, up 1, 2, 3, put our point. Over -4, up 4, put our point. Over -3, up 5, put our point. Over -2, up 4, and put our point. And we can see it would just keep going this direction. So it flipped it, right? It flipped the graph over because there's a negative out here. And because of this minus 3, or minus a negative 3 inside of here, if we wanted to write that, minus negative 3 plus 5, it took the vertex and shifted it to the left 3 and up 5 units. And then the negative again on the outside flipped it over. So there were how many translations here? The negative, the flip is 1, or the reflection. The shift to the left 3 units is a second translation, and the shift up 5 units is a third translation. So we had 3 translations in this graph. All right, so let's look at this next one. Describe how this is related to the graph of the parent function. So I'm going to plug in 1/4. Negative 1/4 times negative 4 is a positive 1. Absolute value of positive 1 is 1. Plug in a negative 1. Negative 4 times negative 1 is positive 4. Absolute value of 4 is 4. Plug in a 0. I get 0. 1/4 times negative 4 is a negative 1, but the absolute value of negative 1 is just 1. So let's go over here on our graph, plot our points. I go over negative 1/4 and up 1. Very, very close here. Right? Over negative 1, up 4. Over 0, up 0. Over 1/4, up 1. Pretend that's closer than that it is. Let's see what would happen if I plugged in 1. Negative 4 times 1 is negative 4. And the absolute value of negative 4 is 4, so I would still get out a 4 when I plug in a 1. So, boom, there it is. So, this 4 stretched it vertically, and this negative just made it a reflection, and it's kind of hard to tell, but this is this line reflected, and this line reflected over here because of the negative value. So again, how would we describe this translation that took place here? It has been reflected across the y-axis because of the negative, and because I multiply by a factor of 4 inside of here, it's been compressed horizontally, which it's easier for me to think of it stretching vertically, but it's a horizontal compression because it's inside of the absolute values. All right, that sums up this lesson. If you have any questions, please be sure to reach out to me. As always, see you guys next time.